Welcome back to I Can Science That, where we've been investigating the concepts of momentum and work. We've been working with a little thought experiment using springs to accelerate masses along a little sliding surface. If you're just joining us now, the original thought experiment involves launching identical masses with different speeds. And what we find is that launching with twice the speed results in sliding 4 times the distance. An interesting question that comes up there is that if that is twice the momentum, how could it be 4 times the work? What is it that a spring has in it that we're releasing here? Are we releasing momentum or are we releasing work? Let's look at it this way. If I took one spring and that gave me 1 unit of momentum, would 2 springs be enough to deliver this 2 units of momentum? I think that's a really interesting question because perhaps the 2 springs would only deliver 2 units of energy and then would fall short of my 4-meter slide. Let's see if we can use just the principles of momentum and this one standard spring, this top spring, as a standard. See if we can apply 2 of those to get twice the speed out of our block. So we'll start with just the one standard spring and our 1 kilogram mass, and we've agreed that this is going to launch us at 1 meter per second. And that's 1 kilogram meter per second of momentum. So what are we going to do to try to get this block going twice the speed? Now, the hypothesis here is that 2 springs would deliver enough momentum to double the speed of our block. But we can't just assume that that's true. This is a mathematical exploration, if you will. So we can't assume that answer because we do have a competing hypothesis. The competing hypothesis is that 2 springs delivers twice the energy. And we know that we need 4 times the energy to get twice the speed. So what is it that 2 springs are going to do? My first thought here is let's just take 2 springs on 2 identical masses and just launch them at the same time. I now have 2 kilograms, and each one is launched by a separate spring. So I know that each one should be launched at 1 meter per second. Now that gives me twice the momentum. However, I didn't get 1 mass moving at twice the velocity. I got 2 masses moving at 1 velocity. But I think we can definitely agree this should work with our standard spring that we've agreed absolutely works. So 2 springs can deliver twice the momentum, but this isn't the configuration I was going for. So my next thought was to launch them in sequence. Let's launch that first block. That should get the first block up to 1 meter per second. That's half the speed we need. Now if I just bump it with another mass, I could bump it and transfer in that other meter per second that I need of velocity. So I'll just launch another mass after it with another of my standard springs, only that's not going to work because the first mass has 1 meter per second, and the second mass also has 1 meter per second. So that second mass is never going to catch up. We're not going to get a bump out of that. What we've ended up with is, once again, 2 individual masses moving each with 1 meter per second. And that's still 2 springs gave us twice the momentum, but it is still in the 2 masses, 1 velocity configuration. So my next thought is that if I use 2 springs to launch 2 masses, I can then use some more springs to separate the masses. So we'll start off. If we launch the 2 blocks with 2 springs, we know that should be able to generate 2 kilogram meters per second of momentum. but that's in the two masses, 1 meter per second. What we have here is this mass is moving at 1 meter per second, and this mass is also moving at 1 meter per second. What I need to accomplish now is I want to get an additional meter per second into this mass, and I'm going to need something to push against, but I've got my other mass here. I can now push against this other mass. If I push with the two springs, I can get another 2 kilogram meters per second out of this thing. And I've got 2 kilograms, and I need 1 meter per second for each one. I just have to push them in opposite directions this time. If I push 1 meter per second this way on this mass, I can use that to transfer the momentum to this mass by pushing 1 meter per second this way on this mass. So by firing those 2 springs to transfer 2 kilogram meters per second in opposite directions, 1 in each of the directions, I should be able to fling my final mass out. I will have left this mass with no momentum. And finally, I now have my 2 kilogram meters per second on this mass in the configuration that I was looking for, which is one mass moving at 2 times the speed. I did it. And I did it using our standard combination of a spring and a mass. So the standard spring that can do 1 kilogram meter per second on 1 kilogram mass, I was able to use with a combination of them to generate 2 kilogram meters per second out of my final 1 mass. However, it took 4 springs to pull it off. And the fact that that took 4 springs should give you a clue about what it is that springs deliver. Each individual spring delivers 1 unit of energy, not a full unit of momentum. If we were to simplify this down now that we know that, all we have to do to launch our 1 kilogram mass at 2 times the velocity is we're going to have to hook up 4 springs to it. We need 4 springs to deliver twice the momentum to the same amount of mass. That was a short one, but really, I think, pretty meaningful. What this shows us with our thought experiment is that according to what we understand from our thought experiment, springs do not store momentum. They store units of energy. And that should, once again, tell you that this unit of energy is a meaningful unit. That's what a spring is apparently doing according to that thought experiment that we started with. We just followed it along to our natural conclusion here. But I thought, since this was a fairly short one, I'd spend a little time to show the slightly more formal version of the mathematics behind this. Here's your warning. If you absolutely detest math, just skip to the end. But if you're just interested to see how we'll use the language of mathematics to explore the world, then feel free to follow along. I'm going to start with Hooke's law. Hooke's law is pretty simple, and it's something that I think all the parties in this discussion have already agreed to. It just says that the amount of force you get out of a spring is directly proportional to how far you squish the spring. You squish the spring more, it pushes back harder. That's all that says. So defining our terms pretty carefully here, we're going to push on the spring with force F. That will cause the spring to squish by this amount, delta X. And this K constant is the spring constant. That tells you how stiff the spring is. And that's just a constant, depends on the material of the spring and how big the spring is, what the spring's made of. You have stiffer springs and softer springs, that's all. So this particular spring has a spring constant of K, so when we apply this squishiness to it, that's how much force it's going to take to squish it that far. And of course, because of equal and opposite forces, that spring is pushing back on us. If we release the spring, it's going to push back and bounce back with that same amount of force that we were pushing. But there's a bit of a tricky thing with that, and that is, as you release the spring, the delta x of the spring's compression shrinks. Right? And this top one, this is what delta x was. So this is the force we had from that spring. But then as it starts to unwind, the force gets less and less until it finally reaches 0 when the spring is completely extended again. That's how the force works according to Hooke's law. And the work equation that we've been working with, the equation for work we agreed was the force times the distance. So we might be inclined to say that this is the amount of force right here, and this is the amount of distance. But the problem with that is the force is not consistent as the distance shrinks, right? The force starts reducing as the distance shrinks down. So in order to equate how much work we get out of the entire spring, or how much work we had to put in to squishing the spring, we're going to have to use a little calculus. We're going to have to integrate. And so the equation we can write is the integration form of work, where force is a function of x. Because it is a function of x, we can't just multiply it times the displacement. We have to integrate that function over the range from 0 displacement. From 0 displacement, we'll integrate over to x and see how much work we put into this spring. So let's do that. I'm just going to replace the force with the equation that we agreed to. And the k here we said was a constant. That's a constant, so we don't need that inside the integral. Here we have our integral ready to go. And we're doing calculus right now at our house. So if you're in high school calculus, feel free to follow along. The integral of x dx is 1/2 x squared. And there's our constant out there. And plus c, right? Don't forget, you're going to get a point off in math class if you don't remember to put the plus c. And then we said our integral is over the range from 0 to delta x. So I've just indicated that right there. And what that just means is we need to plug in this formula where x is delta x and subtract where x is 0. The subtraction, thankfully, just makes the c's drop out. And this term was 0, so that one drops out completely. And we're left with simple equation. The amount of work we put into a spring is proportional to the square of the displacement. And what is this equation telling us? What is this saying? It just says simply, the more you compress a spring, the more work that spring is storing. And if you care, it's proportional to the square of the amount of displacement. The interesting thing about this is that this is consistent. This is a consistent number that has nothing to do with the amount of mass that is on that spring. So that's the work stored in a spring and how we got it. Let's look at this from a different perspective. I would like to calculate how much momentum is stored in the spring. Because remember, the whole question we started with was whether a spring stores energy or stores momentum. If the spring stores momentum, how much momentum is that? So in order to have some momentum, we're going to need a mass. So I'm going to put a mass of mass m. The blue thing now has mass m. I put on the end of my spring. And it's going to be experiencing this force from the spring pushing it. And as the compression of the spring comes out, the force is going to reduce. And what we're going to need to do is integrate that force to calculate the final velocity of the mass. And based on that, we'll know the momentum, right? We know that the force is just going to come from Hooke's law. We know that acceleration is just going to come from F equals ma. And this is the momentum ultimately that we are looking for. So let's jump right in. The acceleration, we know by definition here, is the second derivative of the position the second derivative of position is the first derivative of the velocity. So we could just say, acceleration is dv dt, which just says, that the rate of change of velocity with respect to time. So we had written that before as, the change in velocity divided by how long it took to make that change. Now, in calculus, we have this lovely chain rule we can apply. That the problem with this right here is I don't want to integrate over time. I want to integrate over displacement, right? I want this thing the spring to come out, and I don't actually know how long that's going to take. I know how much displacement that is. So I want to integrate over x. I don't want to integrate over time. So I'm going to apply this little chain rule here. The dv dt is the same thing as dv dx, dx dt. And dx dt is, in fact, velocity. That's v. So I can rewrite acceleration as v times dv dx. So I'm going to do that. And while I'm at it, I'm going to move the dx on over to the other side. So we get a fairly simple looking expression that just says a dx equals v dv. Now, I think the next thing I'm going to want to do, I'm going to integrate that. Let's go ahead and integrate that. And we should recognize, we've been seeing this one before. V dv, well, that's 1/2 v squared. And for the a dx, a is a function of x. So let's go ahead and fill that in. What is it? A is f over m, and f is k delta x. So we're going to have k delta x over m for our a and our 1/2 v squared. And you'll see that I've dropped the plus c's, but on the previous slide, we know where those go, so I didn't feel like we had to keep dragging those along. K and m are both constants, so I pulled them out. And now I have, again, this very friendly integral, which by now I recognize as 1/2 x squared. And on the interval from 0 to delta x, that is 1/2, here's our 1/2, delta x squared, and our constant k over m equals 1/2 v squared. Wonderful. Got rid of all those nasty integrals, got all those dt's out of there. What am I trying to do? I'm trying to get momentum, which is mass times velocity. So let's take this thing and solve it for velocity. The 1/2s, we can drop those, and then we just have to square root both sides. So that's pretty straightforward. The velocity is the square root of k over m times delta x. That's pretty good, but momentum is mass times velocity, so let's multiply mass on there. So we'll have, instead, the momentum is the square root of mk times the displacement. There you go. That is the amount of momentum stored in a spring. And the insight that we get by looking at that piece of math there is that the amount of momentum stored in the spring depends on the mass. It's proportional to the square root of the mass that's sitting on the spring. If we change out the mass, we're going to get a different momentum. And those who didn't want to look at the math can join us again for the summary. What did we discover? What we just discovered was that the momentum stored in a spring is different depending on what mass you're trying to accelerate with that spring. On the other hand, the amount of energy that we stored in the spring has nothing to do with the mass at all. And this tells us simply that springs store energy, they do not store momentum. The energy can be turned into momentum. Absolutely, we can use that energy to accelerate that mass, but the amount of momentum you're going to get depends on what mass you put on the spring. A compressed spring holds a consistent amount of energy no matter what mass you put on there, but that the amount of momentum that you're holding in that spring we don't know how much momentum that is until you put a mass on there. You tell me how much mass it is, and I'll tell you how much momentum you're likely to get out of this thing. So this difference here, this dependency on mass, leads to an excellent idea for a practical experiment. We've seen it play out here today in this thought experiment. You could do a practical experiment. You could take a spring, compress it to a fixed amount of compression, and then push on different masses with that same spring. Compress the spring, put a mass on it, measure how much velocity you get out of that mass. Take the same spring to the same compression and launch a different amount of mass and see how much velocity you get out of it. Does the velocity vary according to the square root of the mass? And if it does, I think you'll see that you have verified this hypothesis. And that's exactly how you could do that, to take that into the real world. Maybe you're so averse to math that you don't want to look at these expressions, these equations, but let me remind you, we did this with our thought experiment. We found that with our standard spring that's able to push a 1 kilogram mass up to 1 meter per second, it took 4 of them to send that 1 kilogram mass down the slide at 2 meters per second. And that's because springs store energy, not momentum.